Hello everyone and welcome to this video on aerial acoustic communication, AAC. In this video, I want to introduce this subject to you and I want to show you our recent research work related to this topic. So let's get started. So first we will see what is AAC system, then we will see the main challenges facing the system, the main research directions, and I want to demonstrate to you our recent research work and illustrate to you how such system might work. And finally, we will conclude this video. So what is AAC? All the available mobile phones around us contain speakers and microphone. These can be used typically for recording and listening to audio signals. However, they can also be used for communication applications, meaning that the transmitter can use the speaker to transmit information in the audio signal, and the receiver can use the microphone to receive this audio signal and to demodulate the information. So simply, AAC is the use of the speakers and microphones that are available on the mobile phones around us for communication applications. The main challenges facing AAC systems are frequency selectivity, meaning that the frequency response of the channel is not constant over the communication bandwidth, which can happen because of the multipath effects and because of the hardware, the speaker and the microphone, in which they don't have flat frequency response. Other challenge is the signal attenuation, in which it limits the communication range. The research directions are increasing the communication range or increasing the data rates, and we can expect that there is a trade-off. For example, if we went high data rate, we can expect that the communication range will be limited, and if we went a long communication range, we can expect that the data rate will be limited and low. So let me demonstrate to you my implementation of the system. I focused on short-range high data rate implementation. So let's go to MATLAB to see the implementation. So I will use this simple GUI to demonstrate the idea. So here we have two main parts, the transmitter part and the receiver part. The transmitter part take an input image, specify the dimension of the image, and we can choose the modulation order. This is the number of bits per sample. We have 1, 2, 4, and 6. Let's choose 2. 2, this means that this is a QPSK modulation. And when we press TX signal, the program will generate the transmitted audio signal, which is an audio file, an audio wave file. We can send this file to a mobile phone to do the experiments. So, for example, let's press TX signal. Here we can see this is the input image. This is an image of Shannon. And this is the frequency response of the signal. So we can notice that the frequency that was utilized is from 18 to 21 kilohertz. We have a sampling frequency of 48 kilohertz. And this frequency range is called near-ultrasonic frequency range. And it's typically not audible, meaning that an adult cannot hear this signal. So what I will do, I will take this audio file that was saved in the file directory of my program, and I will send it to a mobile phone so we can do the experiment. So what I did, I sent the audio file to this phone, and I will use this phone as a transmitter, and I will use this other phone as a receiver. What I will do, I will play the audio on this phone, and I will record the audio on this other phone. So first, let's use use it with short range, this close range, and we will do another experiment with a longer range. So I will first play the audio and I will record it in this other phone. So let's get started. This is the first experiment. I will do another one. And I will increase the range for this last one. So I will, maybe you cannot see the phones, but they are almost maybe more than half meter apart. So I will also do the experiment for this range. So now we have three experiments, two with short range and one with increased longer range. So what I will do, I will send this audio files back to my PC to the directory of the program, and we will do the other part or the receiver part. So what I did, I sent back the record audio from the receiver to the directory of the program. And now let's do the receiver part. So we have three recorded audio signal. First, let's start the first one. So I named it rx1.wave because it's an audio file. So I can press D mode, and we can notice several things. First, we have this image. I think RX1, it is the one that we recorded from the longer distance or from the longer range. So first, we can see this is the transmitted image. This is the received image. It is noisy. There is a lot of bits error. And we can see that from the constellation diagram. This is the constellation diagram. If we zoom in, we can notice this, the QPSK constellation diagram, but we can see that it is very noisy, and we can expect that the performance is not that good. Other thing is this is the power spectral density or the spectrum of the received signal. So we can notice the severe frequency selectivity. Notice the response of the transmitter or the frequency response of the transmitted signal. This is the frequency response of the received signal. Notice how the frequency selectivity is severely affecting the received signal. We also can see that we have, this is the audible frequency band, and we can see that there is other noises. This is not a problem because the receiver will apply a bandpass filter, and it will attenuate all the unwanted frequency bands. So let's see RX2. RX2 is the signal that we recorded from shorter range. We can expect that it will be better. So let's see. And notice, as expected, we have almost no errors. The constellation diagram is perfect, and this is the received signal. Notice the effect of the frequency selectivity is also better from this one. So this is when we used a longer range. Let's close it. So notice that this is the wanted frequency band, and this is the unwanted frequency bands that will be filtered, no problem. And we can see that we have perfect constellation with perfect image with no errors. Let's see the other one. This is also, we recorded it at short range. So let's see. Notice it's also perfect. We have a very good constellation diagram, and we can see that we have a very good received image. This data rate of our implementation was calculated at 5 kilobits per second. The data rate is simply the number of bits divided by the signal duration. So because we have a binary signal, the number of bits is simply the number of pixels of the signal. So this can be increased by simply increasing the modulation order. For example, if we see the data rate when we have 16 QAM, this is 4 bits per symbol, meaning that we have 16 QAM. We can see we can have a data rate up to 9.4 kilobits per second. And this can be increased further if we have 6 bits per symbol, which is 64 QAM, and we can reach a data rate up to 13 kilohertz, 13 kilobits per second. So let's conclude this video. So in conclusion, we had an idea about AEC systems, the challenges facing the system, and the research directions. And we also saw an implementation of the system focusing on the short range and high data rates.